All right, everybody. This is 4.5 differentials and approximations. So let's get started here. We got a graph of f of x with inputs of a and b, this interval here. This would be our output, f of a. And this would be our output here, f of b. All right, so this distance here is commonly referred to as delta y, right? The same is likewise on the independent variable, where this is called delta x. Now what's interesting is we can estimate this delta y, should really stretch down to there. We can estimate delta y by using the derivative. All right, so our derivative, let's talk real quick about that. This is notation for the derivative, as well as dy over dx. Okay, and really the derivative at a would create this tangent line. And so if this were delta y, right, which is just the shifted version of this length here, the derivative can help us. Okay, here's our tangent line. This actually helps us to approximate that change in y, right? So what we call this is dy, right? Because dy, change in y over change in x, is how we refer to the derivative. Now I'm going to manipulate this slightly and find out how we can come up with dy. Well, we'd multiply both sides by dx. So we'd take f prime of x at, let's say, a, right? And multiply it by dx. All right, so let's just kind of dig into this a little bit. So dy, that was really good, is approximately equal to delta y. And that approximation gets better as delta x approaches 0. Right? So the closer this change in x is, the better the approximation for dy would be. Now delta y, a couple of things we want to note, is going to be equal to f of b minus f of a. Therefore, f of b is equal to f of a plus delta y. Now again, delta y can be approximated using dy, so f of b is going to be approximately equal to f of a plus dy. Alright, so we're going to use this concept of dy, right, which we can find dy using the derivative. And we're just going to go ahead and play with that and come up with some approximations of some functions. Okay, so let's do an example real quick using the function y equals x squared. And then after that, we'll use the function y equals the square root of x. So the derivative, let's first of all write in derivative form. Let's take the derivative of this with respect to x, which gives us dy dx is equal to 2x. All right, just a little practice. Finding what dy would equal, we would have 2x dx. All right, so let's jump into example 2 then. So let's find dy for y equals square root of x. You can pause the video right now if you'd like to, or just watch. But I'm going to take the derivative with respect to x, get dy dx is equal to 1 over 2 root x. Okay, hopefully you got that right. Let's go over here and let's find dy. Well, dy would equal, I'm going to multiply both sides by dx, putting the dx on top, I would get this. Okay, so let's say that x equals 1 and dx, which is equal to delta x, is also equal to 1. What that would do is that would make a equal to 1 on our square root of x function and b equal to 2, right? So if a equals 1 and dx equals 1, then b equals 2. So if we want to find or evaluate dy and delta y with these values, what we would do is we would take dy, which equals 1 over 2 root x, okay, and, whoops, up here, dx over 2 root x. Well, dx was 1, nice, that worked out well. and x equals 1 as well. So dy, which is an approximation of delta y, would be 1/2. All right, so how would we find actual delta y? Right, actual delta y we said was f of b minus f of a. Well, we said b was 2 and a was 1, so delta y would equal the square root of 2 minus the square root of 1. Square root of 2 is like 1.41 something, 414 or something, so square root of 2 minus 1 would be 0.414. And as you can see, dy is approximately equal to delta y. Right? 1/2 is pretty darn close to 0.414. Okay, so if delta x was smaller, this approximation would be much better. Okay, so in part C of this question on your notes, it asks to sketch a graph showing the line segments with lengths dx, dy, and delta y. So let's do that right here. So here is the square root y equals square root x. And let's go from 1 to 2. And it's not to scale, but we can handle it. Okay, so here's f of a, right, f of 1, which equals 1. And here's f of b. This is going to be an interesting scenario here just because of how close this is, but we'll work with it. All right, here's our delta x, which we know is equal to dx, right? dx is 1 and delta x is 1. This right here is delta y, okay? And we found that delta y was 0.414. And we know that dy is an overestimate, right? Well, yeah, we know it's an overestimate of delta y. So let's see why that is, right? Here's the tangent line. And as you can see, here is the difference, right? There's the error. That's the difference between 1/2 and 0.414. So this output right here, right? This output right here is 1/2 plus 1. So this is the 0.2 comma 1 plus 1/2. So that's 3/2. All right, this is the output 2 comma 1.414, or the square root of 2. All right, so there you have it. This length here, let's highlight it. This length here is dy, while this length here is delta y. Okay, now the overestimate piece or underestimate piece has to do with concavity. It's an overestimate if the function is concave down. Concave down. It'll be an underestimate if the function is concave up. All right, so let's get to our last example here. Oh, I'm sorry, we're gonna do a little bit more, almost forgot. We are going to approximate, let's approximate the square root of 1.1. Okay, so just as we think about this, let's recall, what is a gonna be here? Well, a is 1, and then if we're approximating 1.1, that makes b equal to 1.1, which makes delta x equal to 0.1. Okay, so be comfortable with that, right? Go to the nearest whole number. Yeah, I guess you could work this a different way and make a 2 and delta x negative 0.9, but that'd just make your life a lot harder. So, okay, recall that dy from the previous problem was dx over 2 root x. Okay, so dy would equal 0.1 over 2 times the square root of 1. Right, of course, a goes in for x, and delta x, which is equal to dx, right, goes in for dx. All right, so it looks like dy equals 1/20th, or you could call it 0.05. All right, so let's work now to approximate y of 1.1. Well, y of 1.1 equals y of 1 plus dy. That's the approximation, so let's work with that. y of 1 is the square root of 1, and we just found dy to be 0.05. So our approximation of the square root of 1.1 is approximately 1.05. I'm just kind of working my way down here. All right, so this, again, the square root of x is a concave down function on its entire domain, so this should be an overestimate. And when I plug this in my calculator, the square root of 1.1 comes out to be 1.0488. Okay, so that's how we can approximate using differentials. All right, I have to reach into my printer to get a piece of paper for the last example. So let's do it. All right, last example is a word problem that says the radius of a disk, we're assuming the disk is a circle, is given as 24 centimeters with a maximum error in measurement of 0.2. That tells us dr is equal to 0.2. Okay, so that tells us that our radius could be anywhere between 23.8 and 24.2. Okay, just values to be aware of. All right, so let's look at the just straightforward, what if the radius, let's talk error for a second here. What if the radius was just 24.2? Okay. Let's see how far off that would be from what the manufacturer hopes that the radius would be of 24, which they're probably marketing. Okay. So a of 24.2 minus a of 24. I'm not doing this in my head, but we would call this dA, right? Or excuse me, delta A. So this would be the exact error, how far off that would be. Comes out to be 9.64 pi centimeters squared. All right, so that would be delta A. But the problem actually asks us to use differentials to estimate the max error. So this, if it didn't say use differentials, that's absolutely fine way to work it. So, but we want you to have a little bit more calculus mind related around this. So I'm going to take the area of a circle, a equals pi r squared. I'm going to take its derivative with respect to r, which gives me dA over dr is equal to 2 pi r. Okay, and I'm going to multiply both sides by dr. Recall that r equals 24, at least we want it to be, and dr is equal to 0.2. So dA would be equal to 2 pi times 24 times 0.2. All right. Again, I'm not a human calculator, but that answer comes out to be 9.6 pi centimeters squared. Pretty dang close, right? Obviously, our calculus version of the error, right, using differentials is an underestimate. That tells me the function is concave up. And if you look at an area function, a with respect to r being equal to pi r squared, that's just a quadratic. That's all that is. Right? It looks like that. That's concave up. So if this is 24 and this is 24.2, clearly the tangent line, right, if this is delta x equal to dx, this right here is dA, or these should be r's. Okay, and this right here would be delta A. Okay, so you can see 9.64 pi is greater, right? That distance is greater than that distance. So according to differentials, this right here, and sometimes the concept can escape you, but this is the largest possible manufacturer. Wow, I'm really good at spelling. Error on the area of the disk. Okay, that is, what lesson is this? 4.5 on differentials and approximations. See you next time.